This is my fourth lecture on chemical kinetics, and today I like to focus the first order reaction kinetics, and it contains two parts. First part is preliminary, and it is meant or it is designed for the higher secondary students as well as NEET and IIT-JEE mains and advanced aspirants. The part 2, my next lecture will be part 2 on this first order reaction kinetics, and that will be more elaborate study and which is meant for the chemistry honors students and the NEET, GATE and also IIT-JEE. So let us now draw an attention to this first order reaction. You know, for the first order reactions, the rate of this reaction is directly proportional to the concentration of this reactant first order, first power or single power of concentration of the reactants. It means that if you make this concentration of the reactant doubled, then rate will also be doubled. So this rate could be written as reaction can be written as A to P. A the initial reactant and P is the product. And the rate is minus D concentration of A by dt equal to K1 and concentration power 1. Single power means it is the first order reaction. So within this small time interval dt, the reactant concentration decreased by dA, and K1 is the rate constant, and K1 is the rate constant. This rate constant is constant for the reaction at a given temperature, unless the experimental conditions are widely varied. So this is the equation number 1, and this is the differential form of this rate law. Of course, if you write this A plus B and giving you P, whether and the reaction say, suppose reaction is first order with respect to A and zero order with respect to B. Then also means this rate of this reaction depends on the concentration, directly proportional to the concentration of A, but independent of this concentration of B. Means if you change the concentration of B, then the rate will remain unaffected, rate will remain unchanged. So in this case also, rate is minus the A concentration by dt equal to K1 concentration of A 1 and concentration of B to the power 0. Since this one is equal to 1, so this will be equal to K1 concentration of A. So this is also the differential rate law for this type of reaction also. However, I like to mention that both this reaction are irreversible. Both these reactions are irreversible, means the reaction will go only in the forward directions, and backward reaction is not permitted, or backward reactions rate of this backward reaction you can neglect or ignore. Further, both this reaction may be elementary, may be elementary. Elementary means a single step. Means this reaction will go in one step to give you the product. However, or maybe the complex. Complex means multi-step. Means this reaction can go in many steps to reach this product. Whatever may be the elementary or complex, it is the first order reaction, and differential rate law will be like this. Now to get the integrated form, now to get this integrated form of this rate law, which is very important for our determination of the important parameters of this reaction, let us integrate this differential equation. This differential equation, separating the variables, we can write minus d concentration A and this concentration coming here and equal to K1 dt. This equation contains two variables, T and concentration A. When T is changed as the reaction proceeds, T is being increased, so this concentration of A is also changing. Now for this integration, this one, and you can write this. You know this integration dx by x equal to ln x, and it is the actually e base x. So in this case also it will be minus ln concentration of A equal to K1 T plus some integration constant IC. Integration constant IC. Whenever after the reaction proceeds to T time, the concentration of A still remaining is A. So, putting the value of or say known condition is that when T equal to 0, concentration of A equal to concentration of A naught. So, putting here minus ln concentration of A naught equal to K1 into 0 plus IC, or IC integration constant equal to minus ln concentration of A naught. Putting this value here, we have say minus ln concentration of A equal to K1T and minus ln A naught. If you remove this minus term from this both sides, then it will be ln concentration of A equal to minus K1T and plus ln concentration of A naught. This is another equation, integrated form of this differential rate law, and which is very important to find out the value of rate constant from this experimental data. So this equation we can write this ln concentration of A equal to minus K1 T and plus ln concentration of A naught, and equation 2. A naught is the initial concentration of A, which we have taken at the start of this reaction. Now, let us first formulate the equations which are coming out from this differential rate law, and then we shall go for the determination of these important parameters of this equation by the use of the different graphs or plots. So in this case also we have, if we bring this one here, then ln A minus ln A naught equal to or if you bring this one here and this one there, then it will be 0 and here A equal to K1T. This one coming to this side minus concentration of A, and this one is coming here, so K minus is removed and K1T, or ln concentration of A naught by concentration of A equal to K1T. You know this ln A minus ln B equal to ln A by B. So this form could be written logarithmic this one. So this is the third equation, ln concentration of A naught divided by concentration of A equal to K1T, and this is equation number 3. Now if we change denominator to the numerator to the denominator, then it will be a minus sign here, and this minus can go here. So it could be written as ln A divided by ln A naught equal to minus K1T. If the denominator is transferred to the numerator and numerator is coming to this denominator, then it will be preceded by negative sign. So negative sign. So negative sign, and this negative is transferred to here. So this one. Or you can write this ln or concentration of A divided by concentration of A naught equal to e to the power minus K1T. Logarithmic is removed, and so here exponential term is coming up. So this one is the fourth equation, concentration of A equal to, or concentration of A equal to concentration of A naught into e to the power minus K1T. So equal to concentration of A naught into e to the power minus K1T, and this is equation number 4. So this is a very important form. If you know this rate constant of this reaction and initial concentration, then at any time after the start of this reaction, you can find out the concentration of this reactant remaining in the reaction vessel. You could calculate from this equation 4. And the equation 5 we can write, say this one coming here, concentration of A divided by concentration of A naught equal to e to the power minus K1T. Now make a negative sign, 1 minus, subtract from 1. This is A, and A naught equal to 1 minus e to the power minus K1T. So, or you can write concentration of A naught minus concentration of A divided by concentration of A naught equal to 1 minus e to the power minus K1T. Now, what is the value of, what is the meaning of this term? You have taken the concentration A naught starting, and this one remaining after this time T. So this term numerator A naught minus A will give you the amount of the reactant converting into product. So this denominator is the concentration of this product, or you can write concentration or concentration of P divided by concentration of A naught equal to 1 minus e to the power minus K1T. So this is another equation. Concentration of this product equal to A naught into 1 minus e to the power minus K1T and K1 e to the power minus K1T. This is equation number 5. Another equation we can write here, say rate of this reaction, rate R equal to rate at this time t dt equal to K1 concentration A. Now putting this value here, this R rate equal to K1 concentration of A naught into e to the power minus K1T. So this is the rate. This is also another equation, R equal to K1 and concentration of A naught into e to the power minus K1T. So this is equation number 6. However, I can mention here that this is the natural log. You can transfer into the common log, 10 base. 10 base by multiplying the 2.303. Say this one. If you convert this natural log to common log, then 2.303 is to be multiplied and log concentration of A. And this is equal to minus K1T and plus 2.303 log concentration of A naught. And you know 2.303 you can eliminate from both sides. So this will be the log concentration of A equal to minus K1 by 2.303 into T plus log concentration of A naught. This also could be used instead of this one. Here also this could be used in terms of this common log. So nowadays actually in terms of this natural log is more popular due to the coming up of good calculators. By means of calculator we can directly use the natural log. So altogether we have these 6 equations. Now I like to draw some graphs to find out the important parameters of this equation. Say of this reaction. Say evaluation of rate constant K1. Let us first evaluate how the rate constant of this reaction could be done. And this is very important. Rate constant of a reaction is very important parameter. And so for this determination you have to do some experiments. Say kinetic data you will have to estimate, and this kinetic data you can write here time t and here concentration of A. When 0 time concentration of A naught and T1 time concentration of A1 and T2 time concentration of A2 and T3 time concentration of A3. Or also you can have this another product. Here concentration of P 0 at this initial time, no product is being formed. Here P1, here P2, here P3. Means by direct experiment, you will have to determine the concentration of this reactant or product at different time intervals, either by chemical method using the titration with a suitable reagent, or by physical method by measuring the physical property of either the reactant or the product which is suitable for your, which is more convenient to you. So what now, to find out this value of K1, let us use this equation 2. Equation 2, this T is variable and concentration of A is variable. Both these two are variables, and you know the T is independent variables and ln concentration of A is dependent variable. So independent variable is plotted along this x-axis and dependent variable is plotted along this y-axis. So it will be this plot. Plot here T, time T, and here ln concentration of A. It will be a straight line, y equal to minus mx plus c. This equation will give you a straight line having some intercept and negative slope. So when t equal to 0 and t equal to 0, this initial constant, the intercept is ln A naught, highest value. This is the intercept, and as t is increasing, this value is decreasing, and it will be straight line, negative slope having some intercept, and this theta, suppose this is theta, so slope equal to tan theta, and tan theta equal to minus k1, and from which k1 you could calculate, and it is the plot of equation number 2. However, you can plot also the equation number 3. Say here T and here ln concentration of A naught divided by concentration of A along this y-axis. Here also T is independent variables and this term is dependent on T. So it will be y equal to mx, y equal to mx. So it will be a straight line passing through this origin with a positive slope. When t equal to 0, so this one equal to 0. So this one equal to 0 means this value starting from 0. So this is theta, suppose. So slope equal to tan theta, and this one the value of k1. So either both this plot are used to determine the value of rate constant of this reaction, which is more suitable for the experimentalist. Now some other plots we can also use. Plot of concentration of A versus T. From this equation 4. Equation 4. So here you along this x-axis time and y-axis concentration of A. When T equal to equation is A equal to A naught into e to the power minus K1T. When T equal to 0, this exponential term becomes 1. So, concentration of A is equal to the initial concentration. So, reaction, the plot will start from here. And as the T is increasing, this one is increasing, this value decreasing, this is constant, and concentration of A is decreasing. So, from the maximum value, as T is increased, this value is decreased and decrease exponentially. As T is increasing, this term decreasing, so A is also decreasing. This one is constant. So, this will be like this. When T equal to infinity, this term is 0. So, A, concentration of A equal to 0. So, at infinite time, the concentration of A equal to 0, means the reaction will be complete in infinite time. So, in a finite time, this reaction will no longer be complete. So, this is the incompleteness of this reaction. First order reaction will never be complete. In contrast, I can mention the zero order reaction. Zero order reaction is complete, and completion time Tc equal to twice the half-life period. But here, half-life period you can also determine from this graph. Say this one is A naught. So, this one is concentration of A naught by 2. So, corresponding time, this time is half-life. Half-life means when the reaction is when the reactant is half decomposed. The time at which the reactant is half decomposed, or concentration of A is cut in half. So, this the half-life period of this reaction you can also find out. You can also find out from this graph. And T half and Tc is equal to infinity. When this reaction is complete, A equal to 0, no reactant, and this one 0 equal to concentration of A naught into e to the power minus K1T, and it is Tc. Completion time, at this completion time, concentration of A equal to 0. So, e to the power minus K1 Tc equal to 0, 0 by something 0, or this one will be, this term will be 0, only Tc equal to infinity, or you can write also 1 by e to the power K1 Tc equal to 0. So, whenever Tc equal to infinity, this one infinity and 1 by infinity equal to 0. So, Tc equal to infinity. Further, we can also draw the plot concentration of P versus T by equation 5. Equation is the concentration of P equal to concentration of A naught into 1 minus e to the power minus K1T. So when T equal to 0, this one equal to 1, 1 minus 1, 0. So P concentration of P equal to 0. At this initial time, at the 0 time, when the reaction has not yet started, the product is automatically 0. Concentration of product will be automatically equal to 0. When T is increasing, this one is decreasing. When this one exponential term is decreasing, 1 minus this value increasing, so concentration of P is increasing. When T equal to infinity, when T equal to infinity, this one equal to 0. This one equal to 0. So this concentration of P equal to concentration of A naught. Means product concentration almost reaching to initial concentration when time is infinity. So the plot will be like this. Concentration of P and here time T, and it will start from 0. And as T increasing, P is increasing and P is increasing exponentially. So this will be like this, and it is almost parallel, and this value is concentration of A naught, So at this infinite period of time, the concentration, initial concentration or the product concentration is equal to the initial concentration. So the another plot also we can draw this rate equal to K1 concentration of A naught into e to the power minus K1T. That means it is the rate at this time T. This is constant. This is also constant. So if you plot when T equal to 0, R equal to T equal to 0 means 1 and concentration is maximum. So this will start here. And as T increasing, R value, it is maximum. As T increasing, rate decreasing. Increasing, this value decreasing, so R is also decreasing. When T equal to infinity, R tends to 0. So this will here R, and this will be like this. Here maximum value and decreasing exponentially. Here also we can make a contrast with the zero order reactions. In case of zero order reactions, rate is found to be constant all along this reaction. Rate will remain steady all along this reaction. Now I set one problem which has been which has appeared in IIT-JEE. So for a reaction with K1 equal to 1.3 into 10 to the power minus 3 second inverse. Second inverse. Find the, if the initial concentration of the reactant is 0.5 molar, find the initial rate and the rate after half an hour. This is the problem, and this problem has been set in IIT-JEE, and in 1 year it will also be IIT-JEE. So let us find out this solution to this problem. So initial rate means R0. You can use this one, equation 6, equal to K1 concentration of A0 into e to the power minus K1 T. Here T equal to 0 initial rate, so R equal to R0. So R0 initial rate equal to K1 and concentration of A0, and this is 1.3 into 10 to the power minus 3 second inverse, and A0 0.5 mole liter inverse. So this will be 7.5. No, this is 5. Let us take it 5. So it is 7.5 into 10 to the power minus 4 mole liter inverse second inverse, and automatically whenever the rate constant is given, unit of rate constant is second inverse, means it is the first order. Rate constant K1, unit 1 by time. This is the concentration, this is concentration, cancels. So unit of K1 equal to time inverse. So whenever the unit of this rate constant is time inverse, say second inverse or minute inverse, it is definitely the first order reaction. So this is the answer of this first part. And in case of second, the R at half an hour, after half an hour, it is also 1.5 into 10 to the power minus 3 second inverse into 0.5 mole liter inverse into e to the power minus 1.5 into 10 to the power minus 3 second inverse into half an hour, means in second it is 30 into 60 second. Second inverse and second cancels. So this rate will be it is actually this rate is 5.235 into 10 to the power minus 5. mole, liter inverse and second inverse. So you see, after initial rate this one, and after half an hour this one, rate is decreasing with respect to time. So this is the preliminary discussion of these first order reactions, and it is meant for, or it is designed for the higher secondary students and also for IIT-JEE mains and the NEET examinations. In my next class, in next lecture, we shall discuss the part 2 of this topic. So thank you all who are watching my video.